Would it ever be possible to solve chess? Perhaps it's just a matter of more computing power. We already have fantastic chess engines that can evaluate millions of positions per second. With ever faster engines and deeper search, surely fully solving the game is only a matter of time? Well, no. More compute and deeper search will never solve chess because the game's game tree complexity, estimated at around 10 to the power of 120 possible games, grows exponentially far beyond any conceivable physical resource, dwarfing even the number of atoms in the observable universe, making brute force determination of every position's outcome impossible regardless of hardware advances. The only real way chess can be solved is if we find a hidden structure we can detect and model. Solving chess means assigning a value to every legal position, win, draw, or loss under perfect play. Imagine each position as a point in space, and its value as a height. You get a landscape. Hills are winning positions, valleys are losing ones, plateaus are draws. Engines don't see this whole surface, they see a small neighborhood, and extend lines through it, extremely accurately, but local. The real question is this landscape structured, or effectively chaotic? The strongest theory we have points toward a kind of chaos. Generalized chess played on an arbitrarily large board, has been formally proven to resist any shortcut. The time needed to solve it grows exponentially as the board gets bigger. This tells us something important. Even though standard chess has a definite answer in principle, the reason we can't find it is that the structure of the game resists the kind of shortcuts that would make it tractable. So if structure exists, it is not obvious, and not easy. However, something interesting has appeared in modern engines. Neural systems like Leela and NNUE don't just memorize positions, they learn compact internal representations. Recent interpretability work suggests these networks can encode short look-ahead patterns internally, effectively storing future board states in their activations. That's a kind of learned structure. A hint that the landscape isn't purely random noise. But it's still local. A learned map of the neighborhood, not a chart of the whole terrain. Does that local structure scale up? That's where it gets harder to answer. Even small changes to the rules produce large changes in overall complexity. Fisher random is a chess variant where the back rank pieces are shuffled at the start. Analyses of these different starting positions show that some setups are dramatically more complex than others. The classical position, regular chess, sits near the middle. This tells us the landscape is highly uneven, not uniform, and not obviously compressible. The fact that tiny rule changes can dramatically shift complexity suggests we're not dealing with a game that has simple global geometry waiting to be uncovered. We do have exact solutions in tiny regions, like 7-piece endgames, captured in what we call table bases. But beyond that, the global structure is unknown. So the question isn't whether we believe in hidden structure. The question is whether we can detect it. Take a large set of positions. Evaluate them with a strong engine. Then ask 3 questions. First, can the value function be approximated using a small number of global patterns? This is the spectral idea. A complex signal, like a sound wave, can often be described as a sum of just a few frequencies rather than tracking every vibration individually. You can apply the same logic here. Decompose the chess value function into mathematical basis components and measure how many you need to capture most of the variation. Modern tools like manifold learning or intrinsic dimension estimation, techniques borrowed from data science, can quantify how low-dimensional the space really is. If a small number of modes captures most of the variation, there is detectable structure. If not, there isn't. Second, if you group positions by coarse features, material count, pawn structure, board regions, do their average values stabilize? And if you group again at a higher level, does that behavior persist? If it stabilizes, chess has macroscopic structure, big patterns that hold across the whole game. If not, it remains sensitive at every scale, and zooming out never simplifies things. Third, can you approximate a position's value as a sum of its local regions? Kingside, queenside, center, evaluated independently. If the error is small, the game decomposes into local parts. If interactions dominate, it doesn't. And in many cases, local evaluations look promising. But the global position is losing, because the interactions matter. Each of these produces a measurable result. Either the function compresses, or it doesn't. There is also a middle possibility, and honestly, it may be the most likely one. Chess may be structured in pockets, endgames, certain openings, but chaotic in the middle game and in general. Some recent work models positions as networks of interacting tensions where small changes propagate globally. That kind of system resists simple decomposition. You get islands of order in a sea of complexity. Engines operate in this local regime, they explore variations and follow candidate lines. That's enough to play at superhuman level. But it doesn't answer the global question. A principal variation is just one path through the terrain. Solving chess would mean understanding the entire surface, so there are two possibilities, or perhaps two and a half. Either the game has a detectable global structure that can be modeled, or the value function is effectively incompressible, beautiful and complex, but without a map, or the truth is somewhere in between, pockets of order, surrounded by irreducible chaos. The key point is, this is testable today, the data exists, the evaluation tools exist. The question can be made empirical. Engines have answered the question of how strong a machine can play. But there is a deeper question. Does chess hide a global geometry, or is it a beautifully complex, incompressible system?